In this video, we are going to go over how to use the saturation tables. So the saturation tables provide the information for your saturated liquid and your saturated vapor data. Saturated liquid is denoted with the letter F. You think liquid, you think fluid. And saturated vapor is denoted with the little letter G, vapor, gas. So it's table A2 and A3 for water. Again, they exist for all the other substances in the back of the textbook. That includes ammonia, propane, R22, and R134A. So the temperature, the only difference between table A2 and A3 is that one is tabulated based on temperature and one is tabulated based on pressure. They give you the same data. It just depends on if you're working with pretty increments of temperature or pretty increments of pressure. So for example, this is table A2, this is table A3. So you can see here we have nice increments of temperature of 210, 212, 220, and our saturation pressures are not very pleasant. Whereas for table A3, we have nice increments of pressure and our temperatures are no longer very nice. If we look at 212, it tells us that our pressure is 14.7 psi, which would make sense as the boiling point of water under standard atmospheric pressure. And if we look at the pressure table, it tells us for a pressure of 14.696, our temperature is 211.99. And if we look here, our specific volume on our temperature table is 0.01672, and on our pressure table we have the same information. The last line of both tables is identical because your saturation tables end with your critical point. The specific volume of a two-phase liquid vapor mixture can be found using our tables and the quality. So let's look at this. What is the total volume of the mixture? Well, the total volume of the mixture is equal to the volume of the liquid plus the volume of the vapor. If I divide by mass, it tells me the specific volume is equal to my volume divided by my mass, which is my volume of liquid divided by my mass plus the volume of my vapor divided by my mass. Now, if we recall, the volume of my liquid is equal to my mass times the specific volume of my liquid, and the volume of my vapor is equal to my mass times the specific volume of my vapor. So I get that I can find that my specific volume is equal to the mass of my liquid divided by my total mass times my specific volume of my liquid plus the mass of my vapor divided by my total mass times the specific volume of my gas. If we introduce quality back into this equation, which again by definition our quality was equal to the mass of our vapor divided by our total mass, and if we note that the mass of our liquid divided by our total mass is going to be the 1 minus my quality, a little bit of algebra yields that the specific volume of my substance at my state is equal to 1 minus my quality times my specific volume, my saturated liquid, plus my quality times my saturated vapor specific volume, which if I rearrange that, I can find out that the specific volume of my gas in my two-phase liquid vapor region is equal to the specific volume of my saturated liquid plus the quality times the difference between the specific volume of my saturated vapor and my saturated liquid. This is sometimes denoted as VFG. Since pressure and temperature are not independent properties in our two-phase region, they can not be used to fix the state. So you have to use quality or specific volume. You need your second piece of information to fix the state, since again, pressure and temperature are not independent in the two-phase liquid vapor dome. So how can I use, we're going to look at how we can use our quality to fix our state. So here's a PV diagram. I have my two-phase liquid vapor dome on there. I have some lines of constant temperature, and I have some lines that mark whether or not I am above or below my saturation temperature. So we look at this. If I know my pressure and temperature, how can I figure out where I am? Well, if my temperature is less than my critical temperature, I'm going to go to table A2, and I'm going to look up and see if my pressure that I'm given is greater than my saturation pressure. If my pressure is greater than my saturation pressure, I'm a compressed liquid. If my pressure is equal to my saturation pressure, I'm in my two-phase region. And I'm going to require a second piece of information to be able to fix my state. If my pressure is less than my saturation pressure, I am a superheated vapor. And I can use table A4. If I was a compressed liquid, it'd be table A5. And if my temperature was actually greater than my critical temperature, I would use table A4 because I am now in the superheated gas range, and whether or not I am a liquid or a gas would depend on my pressure. These relationships all relate to the shape of our isotherms. So for example, at point A here, our pressure is greater than our saturation pressure at the same temperature, which means we are in our liquid zone. So this is the liquid. At point B, my pressure is equal to my saturation pressure, so I'm within the two-phase liquid vapor dome. And at point C, I'm at a pressure lower than my saturation pressure, so I am in the superheated region. Similar rules exist for our TV diagrams. If you look up your temperature and relate your temperature to your saturation temperature at a fixed pressure, however, all of the relationships are flipped, because if we remember, the line of constant pressure on a TV diagram is the opposite of the line of constant pressure on our PV diagram. Now that we know how to navigate which of our three regions we are in, let's look at a quick example using water. We're going to determine our different states based on different criteria. Our first criteria is a temperature of 140 degrees Celsius and a specific volume of 0.5 meters cubed per kilogram. So the first thing I always do is I go to my saturated table. So I'm going to go to table A2, and I'm going to look up at 140 degrees Celsius. VF is equal to 1.0799 times 10 to the minus 3, and VG is 0.5089. And now I'm going to compare the V that I was given to VF and Vg. Well, our volume is greater than the specific volume of a saturated liquid, but it's also less than the specific volume of saturated vapor. And if I am between these two numbers, I am in the two-phase liquid vapor dome. And the property I was trying to find was my pressure. My pressure is going to be equal to my saturation pressure, which is equal to 3.613 bar. The next case we are going to examine is I have a pressure of 30 megapascals and a temperature of 100 degrees Celsius, and I am tasked with finding my specific volume. So again, the first thing I'm going to do is go to my saturation table, which is table A3. And I want to find that table A3 ends at my critical pressure, which is 220.9 bar. Our pressure of 30 megapascals is equal to 300 bar, which is greater than our critical pressure. So now I know I am either a compressed liquid or a superheated vapor, so I want to look at my temperature. Our temperature is equal to 100 degrees Celsius, which happens to be less than our critical temperature, which is 374.1 degrees Celsius. So since T is less than Tc, I am a compressed liquid. So I'm going to go to table A5 and find that my specific volume is equal to 1.0290 meters cubed per kilogram. The next state we're going to consider is we have a pressure of 10 megapascals and a temperature of 485 degrees Celsius, and we need to find our specific volume. So again, I'm going to go to table A3, and at a pressure of 10 megapascals, which is equal to 100 bar, my saturation temperature is 311.1. So my temperature, which again is 485, is greater than my saturation temperature. This means that I am a superheated vapor. So I'm going to go to table A4. If I go to table A4, I'm going to find that sadly 485 degrees Celsius is not listed in the table. So I'm going to have to interpolate. So my specific volume is going to be equal to 0.03160 plus 485 minus 480 divided by 520 minus 480 times 0.03394 minus 0.03160, which is 0.03189 meters cubed per kilogram. The last case we're going to consider is I have a temperature is equal to 80 degrees Celsius, and I'm given a quality of 0.75, and I need to find my pressure and specific volume. Well, it's a dead giveaway. If you are given the quality, that means you are a two-phase. The quality only exists within the two-phase liquid vapor dome. So if you have a quality, you are a two-phase. And since I was given the temperature, I'm going to go to table A2. Since I'm in the two-phase liquid vapor zone, my pressure is equal to my saturation pressure, which is 0.4739 bar. And my specific volume is equal to my saturated liquid specific volume times my quality times the difference between my saturated vapor and saturated liquids. Please note that for water in particular, the values of your saturated liquid in your specific volume are listed 10 to the 3 times larger than they actually are, which is where this comes from. So my specific volume in this case is 2.556 meters cubed per kilogram. In the next lecture, we're going to define enthalpy. So we're going to look up enthalpy in our tables, and we are eventually going to learn how to determine properties for ideal gases.